Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present epoxy acrylate vinyl esters. Vinyl ester resins are thermosetting resins that consist of a polymer backbone with an acrylate or methacrylate termination group. The backbone component of vinyl ester resins can be derived from epoxide resin, polyester resin, urethane resin, and so on, but those based on epoxy resins are epoxy acrylates and are of particular commercial significance. The structure of an epoxy acrylate has been presented here. Vinyl ester resins can be used in neat form, for example with no diluents, or they can contain either a vinyl type reactive comonomer, for example styrene, vinyl toluene, and 3-methyloyl propane, 3-acrylate, or a non-reactive diluent, for example methyl ethyl ketone or toluene. Typically, the methacrylate vinyl ester resins contain styrene and are used in chemical-resistant fiberglass reinforced plastics, where the acrylate vinyl ester resins are supplied undiluted with appropriate co-reactants added during the formulation of ultraviolet cure, coating, and inks. Acrylate and methacrylate functional groups have been presented here for your reference. The physical and handling properties of vinyl ester resins depend on the source of vinyl termination, methacrylate or acrylate, the amount and type of co-reactant, and the type and molecular weight of the resin backbone. Upon cure, the styronated methacrylate vinyl ester resin exhibit excellent resistance to acid, base, and solvents. The acrylate vinyl ester resins are more susceptible to hydrolysis than the methacrylate vinyl ester resins, and thus are not generally used in application requiring premium chemical resistance. Conversely, acrylate vinyl ester resins are preferred in radiation cure systems because of their greater reactivity. Undiluted vinyl ester resins vary from semi-solid to solid and therefore utilizes both reactive and non-reactive diluents to provide workable viscosity levels and enhanced reactivity. Epoxide backbones of various molecular weight are used in vinyl ester resins. Higher molecular weight produce greater toughness and resiliency, lower solvent resistance, and lower heat resistance. Unlike polyester, vinyl ester resins possess a low ester content and a low vinyl functionality, which result in greater resistance to hydrolysis as well as lower peak exotherm temperature and less shrinkage upon cure. Like polyester, vinyl ester resin exhibits a finite storage life that is controlled by the addition of polymerization inhibitors, free radical traps, during the manufacture. In fact, the properties of epoxy acrylate are somewhere between polyesters and epoxy resins. In 1965, these resins were commercially introduced by Shell Chemical Company under the trade name of Epocryl resins. These resins were identified as epoxy methacrylated or acrylated and were shown to provide chemical resistance superior to that of premium chemical resistant polyester resins of that period. In 1966, Dow Chemical Company introduced the Deracane vinyl ester resin designation, which with the introduction of a similar resins for molding applications. In 1977, Interplastic Corporation, an Richhold chemical company, introduced vinyl ester resins under the Resin and Corolite product designations, respectively. Since then, numerous products have been introduced to the market. The backbone of the epoxy acrylate resin can be of various types. In the presented schematic, epoxy acrylate and methacrylate systems of Novolac and bisphenol A resins have been presented. Vinyl ester resins are produced by the addition of ethylenically unsaturated carboxylic acid, methacrylate or acrylic acid, to an epoxide resin, usually of bisphenol A epichlorohydrin type. The schematic of the reaction has been presented here. In the case of the epoxy, the glycidyl era bisphenol A type is used. The reaction of acid addition to the epoxide ring esterification is exothermic and produces a hydroxyl group without the formation of byproducts, for example, as in polyesterification, where water is produced. Appropriate diluents and polymerization inhibitors are added during or after esterification. Epoxide resins that have been used to produce vinyl ester resins include bisphenol A types, general purpose and heat resistant vinyl esters, diphenolic Novolac types, heat resistant vinyl esters, and tetrabromo bisphenol A types, which are fire retardant vinyl esters. For acrylate vinyl ester resins, the low molecular weight bisphenol A epoxies are generally used as the backbone component. Vinyl ester resins, like unsaturated polyester resins, contain double bonds that react and cross-link in the presence of free radical produced by chemical, thermal, or radiation sources. Cure proceeds by a free radical mechanism comprising initiation, or the induction period, propagation, and termination. The rate determined step is initiation. One of the most important ways to synthesize these oligomers is the reaction of epoxy resin with ethylenically unsaturated carboxylic acid, for example, acrylic or methacrylic acid, in the presence of an esterification catalyst. In general, any esterification catalyst is suitable for use to prepare vinyl ester, including tertiary phosphine or amines, metal hydroxides, tin salts, ammonium, phosphonium, or sulfonium salts, and imidazole derivatives. The reaction is usually carried out for a couple of hours at the temperature range of 70 to 120 centigrade with air or N2 blanket to inhibit vinyl polymerization. The preparation method comprises the following steps: adding epoxy resin in a reactor and adding 0.12% to 0.15% of a polymerization inhibitor, and 0.3 to 0.4 of a catalyst at the same time, stirring uniformly, dropwise adding acrylic acid for 1 to 2 hours by using a constant pressure funnel, reacting for 2 hours or for 3 hours at a reaction temperature of 125 to 135 centigrade, and ending the reaction until reaction acid value is less than 5 mg KOH per gram, and cooling to the room temperature to obtain the epoxy acrylate. Mechanical and thermal properties of cured epoxy acrylate resins are very sensitive to the chemical and structural nature of the epoxy resins and crosslinker, the type and concentration of cure initiator, cross-linking reaction conditions in the UV chamber, epoxy conversion, and crosslinker to epoxy acrylate ratio. Epoxy acrylates are characterized by flexibility, hardness, thermal resistance, and non-yellowing. The resin properties of vinyl ester are typically characterized by viscosity, diluent content, and reactivity. Except for the thermal distortion temperature, the mechanical strain, tensile and flexural properties of cured vinyl ester resin coatings vary only slightly as a function of the molecular weight and type of epoxide backbone. Variations in co-reactant type and amount also produce moderate changes in the mechanical strain properties. Generally, these resins show good electrical properties and chemical resistance. They exhibit excellent acid, base, and solvent resistance over a wide temperature range in both resin castings and glass laminates. The chemical resistance of epoxy-based methacrylate vinyl ester resin is higher than epoxy-based acrylate vinyl ester resin, as it has been said. And the excellent acid-base resistance of epoxy-based methacrylate vinyl ester resin is attributed to their low ester content, the protection of the ester linkage by the adjacent methyl shield, and the steric hindrance of the co-reactant, usually styrene. In terms of shrinkage, upon cure, the volumetric shrinkage of vinyl ester resin is generally lower than that of unsaturated polyester resins, but higher than that of their parent epoxy resins. The volumetric shrinkage increases with increased backbone, double bond, and co-reactant content. Because of their high shrinkage values compared to epoxy resins, vinyl ester resins exhibit only moderate adhesive strengths. To reduce shrinkage and obtain maximum strain adhesive formulations are based on vinyl ester resins with low backbone, double bond content, low co-reactant level, and high filler contents. The addition of various rubber compounds to reduce shrinkage also improves the peel strength of vinyl ester adhesives. Their high pigment wetting properties, their flexibility, and their high gloss make epoxy acrylate the right choice for hard and durable paints, high pigment loading paints, and in blends with polyesters or polyurethane resins for lithography and screen inks. Some of the key properties of epoxy acrylate include high strain and hardness, good adhesion to a wide range of substrate, high temperature resistance, good chemical resistance, and good electrical insulation properties. Epoxy acrylate is typically applied using a brush, roller, or spray equipment, and it can be cured at room temperature or using heat and is available in variety of formulation to suit different application needs. UV curing is the process of photo-initiated conversion of polymeric materials from a liquid to a solid. It is a popular alternative to conventional thermal curing. Generally, UV curable formulation contain oligomers or prepolymers consisting of reactive sites based on the functional acrylate group to meet VOC compliance. Epoxy acrylate can be used for applications where radiation cure is required. The polymerization of multifunctional monomers or oligomers by UV curing has become a widely used technology that is found in many industrial applications due to its unique advantages. The coating industry is the most important application of UV curing technology and is used to protect the surface of materials with quick drying varnishes or printing inks. Other uses include manufacturing solder masks, stereolithography, and microelectronic photoresists. In the photopolymerization process, the type of monomer and photoinitiator are of great importance because the compositions can be polymerized using a free radical or cationic photopolymerization mechanism. Currently, free radical photopolymerization is used most often due to the large assortment and low cost of free radical monomers, photoinitiators, and additives to set the final properties, with the possibility of combining them into products with different properties. In turn, the disadvantage of this system is the inhibition of free radical polymerization by oxygen. Cationic photopolymerization is an alternative polymerization method in the production of cured coatings. The cationic process is not inhibited by oxygen, however. Compared to the free radical photopolymerization, it does not stop immediately after the radiation is turned off, but occurs but occurs from darkness, sometimes slower, which is referred to the dark curing. Curing coatings with cationic photopolymerization are often used for monomers that cannot be photopolymerized in a free radical manner, for example, vinyl, ethers, and epoxides. Although both the methacrylate and acrylate vinyl ester resins have been employed in radiation cure application, the use of the latter is preferred in UV cured coating and ink formulation because they are faster. In many UV applications, the cure is completed within 0.1 second. Electron beams and other radiation sources have also been used to cure vinyl ester resins. The major advantages of radiation cure as compared to thermal cure include greater energy efficiency, reduction or elimination of volatile emissions, faster line speeds, ambient temperature cure, low equipment cost, and low floor space requirements. Benefits of epoxy acrylates. They are often very fast cure. Epoxy acrylate accelerate curing time for a faster, leaner, and more efficient production processes. They have a high hardness. The superior hardness obtained through blends with epoxy acrylate results in excellent mechanical properties and durability even under rough conditions. They show excellent chemical resistance. Epoxy acrylates are perfect for dealing with highly acidic or harsh environments. Epoxy acrylate is resistant to many chemicals including acids and bases, which makes it ideal for use in environments when chemical exposure is likely. They are also known for their strong adhesive properties and are often used as a bond agent in the construction, automotive, and electronics industries. They are also known for their high strength and thermal stability. Epoxy acrylate has a high tensile strength and can withstand a lot of wear and tear, making it suitable for use in structural and load-bearing applications. Epoxy acrylates can also achieve high characteristic loads, and they can be specified in applications involving damp substrate or relatively low temperatures. The major disadvantages associated with these materials, however, are the high viscosities and poor exterior durability. Various factors such as molecular weight distribution, and functionality will affect the viscosity, but strong hydrogen bonding through the secondary hydroxyl is reported to be the main cause. The end result is that a formulation often requires a high percentage of reactive diluents to obtain a viscosity suitable for the applications. Capping these free hydroxyl groups reduces the resin's viscosity, but often at the expense of film properties, and modest improvement may also not affect formulation viscosities. Such high levels of diluent can cause film brittleness and shrinkage to become a problem depending on type of the functionality. Here are some common uses of epoxy acrylates. Adhesive. Epoxy acrylate is commonly used as an adhesive for bonding a wide range of materials including metal, wood, glass, ceramics, and plastics. It is known for its high strength and durability, making it suitable for use in structural bonding applications. Coatings. Epoxy acrylate can be used as a coating for various surfaces to protect them from wear and tear, chemical, and other environmental factors. It can be applied to floors, walls, and other surfaces to provide a hard, durable finish that is resistant to abrasion and impact. Encapsulation. Epoxy acrylate is often used to encapsulate electronic components and other sensitive devices to protect them from moisture, dust, and other contaminants. It can be applied in a liquid form and then cured to form a solid protective layer around the device. Casting. Epoxy acrylate can be used to create a custom-shaped parts or components by casting it in a mold. It is known for its ability to produce high-quality, detailed parts with a smooth surface finish. Optical applications. Epoxy acrylate can be used to create optically clear components such as lenses and windows due to its low index of refraction and good light transmission properties. Fiberglass reinforced plastics, it can be used in them. Vinyl ester resins can be fabricated into fiberglass reinforced plastic composites via filament winding, hand-lie spraying, centrifugal casting, bag molding, or pultrusion. Vinyl ester resin-based fiberglass reinforced plastics, for example, pipes, docks, scrubbers, flue stacks, and storage tanks are used by the chemical processing, petroleum, agricultural, mining, and food industries, as well as the utilities. Because they exhibit excellent chemical resistance, low maintenance requirements, design flexibility, and ease of installation. Vinyl ester resin-based composites have demonstrated economy and better price to performance characteristic than steel and its alloys in many corrosive industrial environments. Vinyl ester resins can also be formulated into chemical resistance linings, grouts, flooring compounds, and mortars which can be applied by spraying. Vinyl ester resin based bulk molding components, BMC, or sheet molding components, SMC, are used in compression molded pipe fittings, applications, housings, pump impellers, and automotive components. These compounds typically contain approximately equal proportions by weight of resins, chopped fiberglass, and fillers. Latent catalysts, pigments, mold release agents, and thickening agents are also added to these formulations. The growth of the vinyl ester market can be attributed to the increasing usage of vinyl ester in the various end-use industries, supported by rising industrialization and increasing industrial production across the globe. Moreover, rising investment in the aircraft and aviation industry is estimated to support the market growth. Further, the vinyl resin market is also anticipated to rise owing to the increased use of flue gas desulfurization industrialization, as well as high demand for corrosion-resistant materials for limestone slurry pipes and stack liners in the flue gas desulfurization processes. Owing to the exceptional properties of vinyl ester, including great adhesion, high chemical resistance, and superior anti-corrosion properties, it makes it the perfect choice for manufacturing marine equipment. As a result of the high consumption of paint and coating, the utilization rate of the vinyl ester is also estimated to increase in the coming years in this section. On the dark side, although vinyl ester has a wide range of application in numerous industries, the high cost of the vinyl ester is anticipated to lower the adoption rate in the next years. The building and infrastructure segment is expected to hold the highest market share by 2033. The growth of the segment can be attributed to the growing application of vinyl ester on plywood and other furniture, supported by the increase in housing units and the refurbishment of old houses across the globe. The major players in the market are Inos Limited, Interplastic Corporation, Nivitex Fiberglass and Resins, Polia Composite Resins and Polymers, Poliant SPA, Scott Bader Company Limited, Showa Denko KK, Sinopolymer Co., and Swancor Holding Company. And also Akzo Nobel is another supplier. Thanks for your attention. I hope you enjoyed the video. Please share your thoughts, questions, or comments, and I will come back to you soon. Thank you.